Welcome to 2.8 Part 3 of College Algebra. My name is Gregory Carlson. We're learning about how to find different types of functions. So we have f of x equals 4x plus 10. We want to find f of x plus h, f of x plus h minus f of x, and f of x plus h minus f of x divided by h. And that might seem kind of weird, like kind of random. Why would you do that? But in fact, this is a huge idea in calculus right here. This is kind of the definition of the derivative if you take the limit as h goes to 0. So it's good that we're kind of getting familiar with this, especially this one. This is going to be used in calculus a lot. So again, we have f of x is equal to 4x plus 10. So let's see what f of x plus h would be. This is part A. F of x plus h. What this means is every time you see an x, replace it with x plus h. So we write the 4, and then we replace x with x plus h. And everything else in the function stays the same. So that's 4x plus 10. And we replaced x with x plus h. Everything else stayed the same. This should be acceptable as the answer, but if you get it wrong, they might want you to distribute and get 4x plus 4h plus 10. So there you go. So this is correct, but this is also correct. So either one is fine. Let's do part B. Part B, they want to know what is f of x plus h minus f of x. We already found f of x plus h. That was this line. So let's just write that down. 4x plus 4h plus 10. So that's f of x plus h. Now let's subtract f of x. And f of x, remember, was right here, 4x plus 10. So we're going to subtract all of f of x. Don't forget your parentheses. We're subtracting all of that. So now you distribute your negative sign. So that's going to equal 4x plus 4h plus 10 minus 4x minus 10. And you'll notice we'll have some canceling here. 4x cancels negative 4x. 10 cancels negative 10. So we're just left with 4h. So f of x plus h minus f of x is equal to 4h. Part C. They want us to find f of x plus h minus f of x divided by h. Okay? So we've already found this top part. That was right here. Remember, we found the top part, and we found that it was 4h. So in reality, this is just going to be, the top part is 4h divided by h. And h cancels with h, and we get 4. So for this function, this entire thing is going to equal 4. And there's something really special that just happens that I'm going to go ahead and tell you. Look at this line right here. This is y equals, or f of x equals 4x plus 10. What's the slope of this line? The slope of this line is m, which is 4. And when we did this giant process right here, look what we got. We got the slope. So when you get to calculus, you're going to discover that this is almost the definition of something called the derivative. And the derivative is basically the slope of your graph. And as you can see, by going through this process, we just found the slope of the graph. The process was a little long, but this is going to be extremely powerful with more complicated functions. Very exciting stuff. Let's do the last page, page 32. Although this is the last thing in chapter 2, it is also extremely important. So we've added functions, we've subtracted functions, we've multiplied and divided functions. So what else could there be? Well, there is composite functions. And what a composite function basically is, it's when you take a function and plug it into another function. So you have your function f of x, and we're going to take an entire function to plug into that. Here's the symbol for it. It's FOG. Don't confuse this with the multiplication sign. It's an O. I don't really like the notation FOG. That to me is confusing. Instead, I like f of g of x, meaning we're going to take g and plug all of g in for x in f. That's different than g of f of x. G of f of x looks like this, g of f of x, meaning we're going to be plugging f into g. So that's why I like this notation a little bit better, because it's easier to see what's happening. So just know that if they say f of g, that means you're plugging g into f. If you see g of f, that means you're plugging f into g. So let's look at an example. Here I have f of x, and here I have g of x. So let's find out what f of g and g of f would be, and let's go ahead and find their domains. So f of g of x is going to equal, now here's how you want to do it. Start by writing out the f, and then every time you see an x, you just replace it with all of g. So because f is the square root of x, we just replace that with, we replace the x with g. And that's the answer. That's f of g of x. The domain of this needs to be bigger than 0, and so if you solved 2x plus 3 is greater than or equal to 0, you would get that x, the domain is x has to be bigger than or equal to negative 3 over 2. If you're confused about that, I did something similar earlier on in this lesson. So the domain of that is x is equal to negative 3 over 2 or bigger. Let's now find g of f. You're going to notice this is a little different. So g of f of x is going to be, we take the g function now, and every time we see an x, we replace it with the f function. So in other words, we get 2. Start by writing the parent, 2, and then every time you see an x, replace it with all of f. So there's g of f. So look at the difference between f of g and g of f. Notice also the domain is going to be different as well, because in this case, we had 2x plus 3 in the square root, but here I only have the square root of x. And so in this case, x just has to be bigger than or equal to 0, because we only have x in the square root. So the domain of this one is 0 to infinity. So that's a little easier. So that's how you find f of g and g of f. Let's do that one more time. Here I have x to the 4 plus x to the 3 as f of x. And g of x, I have 2x minus 3. So let's find f of g of x. Remember that that's the same as take f and plug in g every time you see an x. So I see right away I have x to the 4, so I replace x with g. So that's going to be 2x minus 3 to the 4th power. Remember, I'm following f, so next I have a plus. Then I have x to the 3rd, but we're replacing x with g of x. So that x gets replaced by 2x minus 3 to the 3rd power. Okay, we cannot add these because they have different powers. You could simplify this a little bit by foiling this out and foiling this out. If you wanted to, it'd be a lot of foiling because it'd be 2x minus 3 times 2x minus 3 times 2x minus 3 times 2x minus 3 for that. So I'm not going to do that. I'm just going to stop right there. So that's f of g. What would the domain be? Are there any restrictions? I don't see any square roots. I don't see any fractions. So those are the only 2 restrictions we've looked at so far. So there's no restrictions, so the domain is going to be all real numbers. That's nice and easy. No fractions, no square roots, so our domain is easy. Let's do g of f now. Remember, that means g is our parent, and every time we see an x, we're going to replace it with f of x. Okay, so let's start with g. It's 2x minus 3, so that's 2. We see an x, so we're going to replace that with f. And then minus 3 at the end. So one way you can do this is, if this is kind of confusing for you, is start by writing your parent function. So write g, which is 2x minus 3. And then just erase x. and put in x to the 4th plus x to the 3. And that's essentially what we just did to get that. Or write f, and then just erase x and write g, 2x minus 3, erase x and write 2x minus 3. I don't like doing that erasing, so I don't do it that way. What's the domain of this? Are there any restrictions? So there's no square roots, there are no fractions, and so once again the domain is going to be all reals. All real numbers or negative infinity to infinity. And that is chapter 2. We are getting through college algebra. Composite functions are extremely important. They help us model some very complicated things. For example, one application of this is, say you're modeling a disease, and the amount, like for example, HIV, say you're modeling that, and the amount of HIV that's grown is going to be based on the number of immune cells that you have, because HIV grows inside of immune cells. So your growth rate of HIV is going to be dependent on the growth rate or decline rate of immune cells. And so to properly model that in a patient, you would need the function of the HIV and you need a function of the immune cells. So maybe in another video, we'll look at some examples of applications of how you can use composite and regular functions. So know how to add, subtract, multiply, divide. Remember, this does not mean multiply. It means plug G into F. This means plug F into G. I hope this was helpful. Hopefully now you're going to be ready for the Chapter 2 review and the test. If you're not in my class and you like this video, I hope you'll like and subscribe. Make sure to leave any questions in the comments or any suggestions. And I will see you in Chapter 3. See you then.